Hello, this is Senior Design project number 21079 for the catalytic removal of carbonaceous particles. The project is sponsored by the College of Engineering under the Chemical and Environmental Engineering Department. I am Ayman Al-Haji and I had the pleasure to work with Anas Sharafi, Lenny Wong, and Mohammed Al-Msabbeh. The project objective was to design and optimize a compact catalytic reactor model that can simulate the capture and removal processes of carbonaceous particles generated from incomplete combustion in diesel-powered vehicles. The model also ensures that the vehicle meets or exceeds the Environmental Protection Agency's current standards while staying within certain criteria and constraints. Exhaust emission standards have been increasingly strict, especially for diesel engines. The concerns from governments around the world are due to the particulate matter or soot emitted into the atmosphere from incomplete combustion of fossil fuels. These particles have severe effects on the environment and human health. The diesel particulate filter (DPF) was designed to capture and remove the exhaust soot in order to reduce the emissions from diesel engines. The team divided the project into two design phases. The first was the design of the physical features of the filter, which included choosing the substrate material and optimizing the dimensions of the filter. The second phase was the design of the chemical features, which included modeling the reaction occurring within the filter walls and optimizing the selection of the catalyst and the temperature of the reaction. Now, I'll leave you with Muhammad to explain the methods of approach.
The method of approach to find the optimal design was to divide the project into two aspects: the design of the physical features and the design of the chemical features. First was the design of the physical features. A wall flow monolith was the base for the design. The substrate material chosen for the filter was the corderite ceramic. The number of channels within the substrate, optimal surface area, and overall volume of the filter were optimized to fit the design. Here are a simulated picture of the substrate inside the DPF and the PNID of our design. Second, the design of the chemical features included developing a one-dimensional mathematical model for a chosen engine, which is 3.0-liter Dynamics I6. The mass balances of the oxygen and particulate matter, including the overall energy balance, were constructed within the control volume as shown in the figure below. These mathematical equations were used in the simulation to finalize the optimal design for the project and determining the catalyst to avoid accumulation within the DBF. COCOMO was used as a method of approach to estimate the cost of the simulation software by predicting the effort and the duration needed to build the simulation software. Now I will leave you with Anas to talk about the results.
After running the simulation software, three graphs were generated and analyzed. The temperature profile indicates that the design operating temperature was at 585 Kelvin and did not exceed a 773 Kelvin operating temperature limit. The concentration profiles of PM and auto match the EPA requirements and prove that there is no net accumulation within the walls of the DBF. The design PM concentration was at 0.02 gram per mile, matching the EPA requirements. The capturing rate was approximately equal to the removal rate at 0.054 mole per meter cubed second, with an error percentage of less than 1%. These results were produced utilizing the optimized parameters shown on the table. The activation energy found during the simulation iteration process was around 40,000 joule per mole. The chosen catalyst for this design was a mix of platinum, ceria, and zirconia. Any other catalyst that would fit this simulation criteria would also work with the optimized DPF. Now I will leave you with Lenny to conclude this video.
The rate of capture of the particulate matter had to equal the rate of reaction inside of the diesel particulate filter to ensure steady-state operation so that there is no net accumulation within the walls. The simulation iterated the reaction rate of particulate matter until it was equal to the capture rate. The simulation proved that the chosen design of the physical features along with the design of the chemical features met the Environmental Protection Agency's standards for particulate matter of no more than 0.02 grams per mile. The COCOMO-based cost modeling for the simulation was used to show the cost of producing the simulation to predict the particulate matter emissions from a diesel particulate filter with user inputted parameters. The simulation achieved the desired results with the chosen physical and chemical design of the diesel particulate filter with an estimated cost of $709 for the simulation. This project has not only been insightful, but very fun for everyone in this group. This project hit home because we are surrounded by vehicle emissions daily. The amount of effort involved to optimize the system to capture the particulate matter was extremely demanding. It deepened our understanding on the design, optimization, and the initial research involved for a project of this caliber. This has been such a great experience, and we hope that a system like this can make a positive impact on the environment. Thank you for watching, and a special thanks goes out to Dr. Ogden, Dr. Brush, and Dr. Shadman, who had spent countless hours dealing with our Zoom meetings and massive amounts of emails with questions and complaints. Thank you.